you guys did really well on your Trig test, your oral exam. And part of that was making sure that you guys were familiar with an angle in standard position. So here is the vertex. This is where the two rays meet. And then I have the initial side of my angle, or the initial ray. It's always on the positive x-axis here, and here's my terminal ray. This one is immovable. It does not move. And this one moves around, and you can go all the way around, you can keep looping around. But for today, I'm just going to stay between 0 and 90. Where's 90? Oh, there it is. So I'm just going to stay in quadrant 1. So why did I make such a big deal about angles in standard position? Well, now we're going to use this format, this angle in standard position, to talk about why angles can be, why you can have the sign of an angle that's bigger than 90 degrees, or you can have the sign of an angle that is negative, less than 0. But for today, just as an introduction, we're going to stay here in quadrant 1. So the first thing I want to do is I want to convert this angle into a right triangle. So to do that, I am going to drop an altitude. And I'm going to drop it from a point here on my terminal side of my angle, and I'm just going to come down to so that it's perpendicular to the x-axis. And now you can see that I have this right angle, and just to convince you, I can even measure it. I mean, I imagine you believe me, but here we go. We'll measure from C to D to A, and you can see that it is indeed 90, and it doesn't matter where that terminal ray is. Can be really, and it doesn't matter how short or long the distance is from the vertex to C. I can be really, really close, and you can hardly see it, but it's still 90 because it's overlapping with this angle. Or, I can be really steep, and anyway, so here is my right angle. And now, obviously there's my third angle of my triangle is right here, angle ACB, and I guess I can even draw that in for you, or have the computer calculate it for you. So here we go. This is the third angle. We have this angle, our right angle, and the third angle of the triangle. But we actually don't really care about this angle so much. What we care about is that this is 90, and this is the angle that really matters for us. So, oops. So I just am going to delete that angle because we don't really care about it. Obviously, we can calculate it. It's 180 minus 90 minus this, or just 90 minus this. But here is our important angle. Okay, so I added a few more details to this applet I was using. Now I've drawn in this perpendicular line. I've made it red, and maybe I should label my angle. I'm sure you believe me that this is 90 degrees, but it's always good to be cynical. Okay, so that's 90 degrees. And so it doesn't matter. Oh, sorry, this is 29.99. I can't quite get it to be 30. We'll get 30.05. That's close. But I have this applet telling me here's my angle A, and it's actually calculating the length of the opposite side divided by the hypotenuse. Now we have a right triangle, because before, without this red line, it was just an angle in standard position. But because I just put a point on the terminal ray and dropped an altitude down to the x-axis, now I've closed it off to be a right triangle. So it doesn't matter how big or small I make that triangle. I mean, excuse me, I'm so sorry. Just imagine that's 30 degrees. I know it's bothering me, so it's probably bothering some of you too. Good for you. But let's say I go out to 12. So I go from 0, 0 along the x-axis to 12. So this length is 12. This is 30. Well, imagine this. Then this would be 60, and then this is 90. If you know the three angles of a right triangle, and one side, you can solve for these two. You can use your trig values. So we could use tangent of 30 and then do x divided by 12, and then you can get this side. Or, this applet is just calculating it. And also you can solve for the hypotenuse. When I take the opposite side, 6.94, and I divide it by 13.86, if you did that in your calculator, you would get 0.5, maybe 0.001. I don't know. It's not exact because this number is a little bit wrong. But then if I go down and I cut this triangle in half, I cut the lengths in half. So now I go from 0 to 6. I've cut this length in half and the hypotenuse length in half, but they're in proportion. So no matter what this length, the hypotenuse is always twice as big if you have 30 degrees here. And if you remember how we derived this by cutting an equilateral triangle in half, it makes sense that this side is half. That's why the sine of this angle is always a half. So it doesn't matter how big or how small, do you see that this is not moving? Now it does matter if I lift this up. Now you can see that sine is changing. If we go to 45, of course I won't get it exactly right. Oh, I did, 45. There is, now I have this, let me make this a little bit. Let's say this is 10. Then this side is also 10 because this is a square that we cut in half to get the right triangle. Well, this hypotenuse is 14.14. That's this times the square root of 2. That's just the way this always works. So, you can use Pythagorean theorem, 10 squared plus 10 squared equals hypotenuse squared. And then you solve, and this is 10 times square root 2. So sine of 45 is this, divide by that, 1 over square root 2, or you can rationalize it and get square root 2 over 2. The same with cosine, yeah? The same. So really, it doesn't matter how tiny, you see that these numbers are not moving, or how big I make that triangle. The sine, cosine, and tangent, it does not change, as long as this angle stays the same in a right triangle. Okay, so for the third and last graphic or applet that I'm going to show you, this kind of pulls together why we're going to do this, use this concept of making the hypotenuse of our right triangle equal to 1. So let's go to 30 degrees. All right. So here I have an angle in standard position. Here's my initial ray, and here's my terminal ray. The lift up is positive. It's going counterclockwise, so it's 30 degrees. And this is standard in trig, and I'll show you why this is important. But some really smart person was like, you know what? I am going to go out on this terminal ray, and I'm just going to go out 1 unit. I'm just going to, we're just going to go out 1 unit and then put a point P. Now, the terminal ray continues. Rays go on forever, but right here, we're going to stop. And so, sine of 30 degrees. You guys proved this to me in on your oral exam. Most of you knew this. Sine of 30 degrees is a half. So it doesn't matter if it's a really small triangle or a really big one. If it's 1 over 2, 4 over 8, this side is always half the side of the hypotenuse. If the hypotenuse is 1, half of 1 is a half. Sine is 0.5. Sine of 30 is 0.5 divided by 1, which is just this side. And this is why this is a really smart idea to make the hypotenuse of this right triangle equal to 1. Because now we know how high, if this is 30 degrees and this is 1, from the x-axis up to this point P, this length, this distance is a half. And cosine of 30 is adjacent over hypotenuse. This is a bit of an icky number, 0.87, but if you remember from the table I had you guys memorize, cosine of 30 degrees is square root 3 over 2. If you put that in your calculator, you get 0.87. So the length from 0, 0 out to where this altitude intercepts the positive x-axis, this length is square root 3 over 2, or it rounds to 0.87. And why is that cool? Well, I'm kind of a nerdy math person, but what is the coordinate of this point P then? Well, how far does it go on the x-axis and how far does it go on the y? On the x-axis, from here to here, it goes square root 3 over 2, and on the y, it goes up a half. If I turn this on, guess what? This is actually, and I mean, it must make sense to you now. This value, the x-coordinate, if the hypotenuse is 1, the cosine of 30 degrees, because that's how far it goes out. How far does it go up? Well, that's the opposite side from 30 degrees. It goes up a half. So sine of 30 degrees is a half divided by 1. So this is just, this is the x term and the y term. This is just, I remember it like x and y is alphabetical. This is cosine of 30. This is sine of 30. So the cosine is of whatever angle you're looking at is the x coordinate of P. The sine of whatever angle you're looking at is the y coordinate of P. So if I move this, let's say I go to 45 degrees. Well, this is, remember how we figured out sine and cosine and tangent of 45 degrees. We had a square, which we cut in half to make a right triangle. So this side equals this side. 0.71 is square root 2 over 2. This is rounded. Sine of 45 is opposite over hypotenuse, or just this. Cosine is adjacent over hypotenuse. So these are the same. Cosine of 45 degrees is square root 2 over 2. Sine of 45 degrees is square root 2 over 2. And let's go to another one that I had you memorize, 60. So now this is just switched. So now cosine of 60 degrees is the x-coordinate of point P. It's a half. Sine of 60 degrees is the y-coordinate. That's how high up it goes. This is the opposite side, the length of the opposite side. 0.87 or square root 3 over 2 divided by 1. So this is how we do all sorts of things with these trig values. This is how we graph them. We use this information and this idea to go forward with making graphs of sine, cosine, and tangent. And also, this is going to be really, really important when we want to find out the sine of 150 degrees. So that's it for this week. I'll see you at the live session and we'll talk about this a bit more. Thanks you guys so much. I'll see you on this week's live session.